In this video, we're going to learn what a maximum and minimum gradient is, how or why we need them, and how to make them and calculate them. So a gradient. What is a gradient? It's just a fancy word for slope. Or like, for example, a truck. When you're driving on the road, they often have signs for trucks that say a grade of 8% or whatever, and it says how steep the slope of the hill is. Similarly, gradient is for a graph is just a fancy word for the slope of that trend line on that graph. So here's an example graph, and it's apparently a velocity time graph. And we have here data points, right, and a nice trend line. This trend line has a slope and everything. So why exactly do we need a maximum and minimum gradient? Well, let's take a look at some individual points. If you look at an individual point, right, there's these error bars, and this is the error bar in your vertical direction, or in other words, the error in velocity, okay? And then it also has error in the horizontal direction, which in this case is error in time. And we measured the time for this data point. We measured the velocity for this data point, but we're uncertain about it. So this data point could be anywhere up here or all the way down here. It could be anywhere over here or over here. We're not exactly sure where it is, okay? So it's somewhere in the box. Now we measured it to be right smack dab in the center, but we're saying we're uncertain, right? And the error bars show how uncertain. And so the actual data point, in real true life, it could be anywhere within this box. All right, now similarly, that's the same with all of these. We're going to take a look at another box, right? The very last point over here. Also, this data point has so much uncertainty and could be found anywhere in this box. We're going to look at specifically when we do maximum minimum gradients. We're going to look at the first point and the last point. Now the reason is because we're going to say, hey, look, if this point, right, was here and here, the trend line makes sense that it should be this one that we've drawn. And so this is the trend line for our data. This is what we believe actually happened. However, we should acknowledge that the trend line could be steeper. For example, if this dot right here, or this data point right here, wasn't at this spot, but was all the way down and over here, right? That would make a steeper trend line. So this data point could be all the way down here, and over here would make it steeper. Where would this data point be that would make it the steepest? It'd be all the way up and all the way over here. So connecting this possible point, right, the data point could be here, connecting this corner to this corner, because the data point could be down here, would give you the steepest possible slope you could get. And so if we draw that line and we say, okay, that line right there would represent our maximum gradient, and if we calculate the slope, that will be the gradient of the steepest possible line. Now, where would we draw a line that would make it the shallowest, right? So, or the least steep. So that would be if we went up here and we come back, right, to this, from this corner to, on this one, it would be if we came to this corner, right? So here to here should be the least steep. So the slope of this line would be our minimum gradient. Now this, whatever this gradient is, whatever this slope is, will be smaller than the gradient of the actual calculated line, and the maximum will be greater. The slope of this maximum gradient will be greater than the slope of the actual line. And so it's like this equation for our trend line that has a slope has some uncertainty to it. And the graph could go, the slope for this line could go all the way up to, possibly all the way up to this, the slope of this maximum gradient, and the slope of the actual value that we measured could go all the way down to whatever the gradient of the minimum line is. So this is, maximum and minimum gradients is like the uncertainty of our slope for our equation. So let's go over how to actually calculate the amount of slope that your maximum gradient has. So for this particular one, or picture, I've kind of simplified our graph, and just for visual purposes and learning purposes. And I've taken out the middle data points because all we really care about is the first and the last one. Now keep in mind that this method isn't a perfect method for figuring out your maximum minimum gradient or the uncertainty in your slope. However, it will be a good a good approximation and works a lot of the times for what you would expect. So it's a good enough result that we'll feel comfortable using it for what we do. All right, so how do I find the slope of this maximum gradient? Well, I've got to just find the slope from this point to this point. As we know, slope is simply the rise over the run, right? So that means we need the coordinates for this point and the coordinates for this point. The coordinates for your center point is, we're going to just call x1, so position for trial 1, and y1, the y position for trial 1, the y coordinate for trial 1. And this is x5, y5. That's just our notation. All right, then we say, okay, so for this, if I want, instead of this point, if I want this point down here, for y, right, it'll be your y1 value, whatever that is on your coordinates for y1, minus whatever your uncertainty is, so you can go down. That's why the coordinate for this point right here says y1 minus delta y, uncertainty in y. And then to get over to this spot, right, to go over to this side, the coordinates will be x1, okay, plus delta x1, right, because you're going up on the horizontally. So this is x1 plus delta x1. Similarly, this spot here will be the y position or coordinate will be y5, and then in this case plus delta y, right, to raise it up. And the x position will be x5 minus delta x to get it over to this position because it's moving down horizontally. This is the equation that you can use every time to calculate it, and then you just got to plug in your. So let's actually see an example where we actually calculate the maximum gradient, because sometimes the concept gets a little confusing when we try and apply it. So let's say I was doing an experiment where I was trying to investigate how the radius of a ball affects the surface area of that ball. Now, here is some data that I might have collected, right? So for this radius, I have this surface area. This is the uncertainty, right, for that radius, and this is the uncertainty for that surface area. Now, I only care about the first and the last point, so I'm only going to look at the top row and the bottom row. Okay, those are organized from first to last, right? So this is my first data point, this is my second data point. So we're going to just plug in the values. For rise is going to be your final y position, that would be up here, minus your initial y position. So we're going to take this y coordinate position here, y5 plus delta y5. So let's look for that. So we say y5, where's y5? So here's your y coordinate. This is your surface, your average surface area is your y variable on your graph. So this is y5. Notice I plug that in. And then I'm supposed to add your delta y, right? So it goes up. So 318 plus 5 is the first part of this equation. And the first coordinate, or the last coordinate on this line. And we have to subtract that from the initial spot, right? So we're going to subtract it from this coordinate here, which it says y1, 32, and then it says minus delta y. It also says it right here. So 32 minus 5. So 318 plus 5 minus 32 minus 5. Now be sure to follow order of operations when you do calculate this and add these together first, subtract these together first, and then subtract this from that, okay? All right, so then we fill out the top row. We're going to do the same thing with the bottom, right? So we say x5 minus delta x, so x5, 5 is the fifth trial. Delta, or x5 is the x value on the fifth trial. So this one, 13, and then it says minus its uncertainty, so minus that. So 13 minus 0.7, great, we did that right. And then it says you subtract it from the first point, which is x1, position x1, plus delta x1, plus its uncertainty, right? So this should say 1.4 plus 0.2. Then we do our calculation, and you do get our sig figs right, and we see that the answer is. Now we're going to follow a very, very similar process when we're finding the calculating the minimum gradient, okay, except it's just the signs are switched, right? So instead of where before maximum gradient this was plus and that was minus, right? You actually just switch the signs. This is now minus, that's now plus. But the concept is all the same, right? I'm doing, except for this red line is the minimum gradient, I'm doing final y position minus initial y position. So this value, y5 minus delta y minus y1 plus delta y, or its uncertainty. And I'm just going to find the rise, and then I do the same thing with the run. So same kind of concept. Let's run through another example of calculation. So with the same chart and the same information, we're going to do the same thing, right? So this time y5, 318, and this time minus your uncertainty, so 318 minus, and then minus your y1 up here, 32, this time plus your uncertainty, so 32 plus 5, etc., etc. And I've just got to fill out the information. In the end, I will get my calculation. Following the rules for sig figs each step of the way, I'll find that I need 3 sig figs in the end, and my minimum gradient turns out to be 22.1.